Hello everyone, welcome to lecture 6 of the course on reinforcement learning. I'm Dhiraj Madan and today we'll be looking at a new algorithm for optimizing our value function which is known as policy iterations. Okay. Let me just recap what we have done so far. So we started with an introduction of the formulation of Markov decision processes. So a Markov decision process consists of the following elements in general. So there is a collection of states or state space, a collection of actions or action space, a reward function, a transition function of next state given the current state and the action, and a discount factor gamma. And so this discount factor is less than 1. Okay. And we have seen that our goal in the goal of an agent in this formulation is to essentially choose a policy. So a policy could be a function from states to actions, or it could be the probability of the choice of action given the current state. So one needs to choose this policy so as to maximize the expected cumulative sum of rewards. So this cumulative sum of rewards is exponentially weighted by this factor gamma to the power t. And this is conditioned on current state being the initial state being S. So first we looked at the idea of evaluation of policies. So essentially, this is policy evaluation. So essentially, given a policy pi, okay, one needs to compute V pi of S as the expectation over pi sum of RT gamma to the power t given that the current or the initial state is S. So how do we do that? We saw that this V pi S satisfies a set of equations which is known as Bellman's equations. So what are these Bellman's equations? So essentially that V pi of the state S, essentially the reward you get of the state S plus gamma or the discount factor times sum over the next states S prime, P of S prime given S and pi S, and then V pi of S prime. Okay. So we have one such equation for every state. And here essentially again all the number of equations as well as the number of variables is same as the number of states. In order to show uniqueness and convergence, right, we had to use the idea of fixed point iterations. We saw that for gamma less than 1, we have a unique solution which always exists. Okay. And next we introduced the idea of optimal value function, which is V star S. So the optimal value function is defined as max over all the policies, expectation over pi, sum over t, RT gamma to the power t, given that the current state is S. Or you can also write it as max over pi V pi S. So how do we compute this optimal value function? Well, this optimal value function also satisfies a similar set of Bellman's equations. The only difference is that instead of following the policy pi, you choose an action which maximizes the value, the expected value of the next state. So we have max over A, sum over S prime, P of S prime given SA, V star of S. So again, this is satisfied for all S. Note that now these equations are non-linear. So we cannot use Gaussian elimination. We always have to use here we are forced to use the iterative algorithm to compute these optimal value functions. And that is what we saw in the last lecture. So the following is the algorithm for computing V star S. Essentially, we initialize T as 0, okay, VTFS as 0 for all S. And next we repeat until convergence. Yeah, so pencil is giving some trouble today. Okay, so what are the steps we are going to repeat? So VT plus 1 of S is RS, the reward we get at the state S, plus gamma times max over A sum over S prime, P of S prime given SA, and VT of S. Okay, and then we update the STs. Okay. So essentially, from here we get an approximate solution. So basically the convergence, although we are saying repeat until convergence, this convergence is usually approximate in the sense that whenever the change in all the states, the value function of all the states is less than some precision epsilon, we say we have converged, right? So this convergence is usually approximate, and this gives us an approximate solution to Feldman's equations. From this, we can recover an optimal policy. Okay, it's quote unquote optimal because okay, it's assuming the solution is exact, it would have been optimal, but otherwise it's a good or fairly good policy, which is argmax over A sum over S prime P of S prime given SA V star of S. So V star, if it is optimal, then we'll get an optimal policy. So what are some problems which we see with this value iteration approach? So firstly, the solution, it's not an exact algorithm, right? So the convergence is approximate. That's the first problem. And secondly, the V star which we have computed, it may not correspond to any policy. So, so there may not be a sort of policy pi, that is, there may not exist policy pi such that V star is. So of course, if V star is the exact optimal solution, then we can compute the optimal policy, right, as above. And this will be, V star will be equal to V pi star. But in general, if it's an approximate solution, then we may not have this, right? If V star is approximate. So if it's an approximate solution to Bellman's equation for optimal value function, then we may not be able to get a policy such that V star is the value function corresponding to a given policy. So these are some of the problems we see. Okay. So now let's try to motivate the idea of policy iterations. So the idea is as follows that, okay, so let V from S to R be just a function. Okay, it may correspond to a value function for some policy, it may not. Now from this thing, let's try to compute pi of s, or a policy which works by assuming that this is an optimal objective function, an optimal value function. Okay, then what is the action to pick? So let's pick the argmax over a of this quantity. Uh, Sum over s prime, p of s prime given as a v of s, right? So we saw that, if v star is an optimal value function, then the optimal policy will be given by argmax over a sum over s prime, p s prime given as a v star s. Why is it so? Because optimal value functions satisfy this quantity, and hence, the policy must pick the action which maximizes this expected value of the next state. So that's what we should be doing. So suppose v is any function, and let's compute a policy which tries to optimize for the next state, the value of the next state, assuming that this is the optimal value. Okay. So let's say we have done that. And let's say in the next step, let's compute v of pi. So what I'm doing now is that I compute a value function which is given by the Bellman's equation, which is satisfied according to policy pi. Okay. So compute v pi using Bellman's. Okay. So we start from some function, and then we compute a policy assuming that function is optimal, and then we try to compute a value function assuming that we are following that policy pi. So now here's a question. Okay. So is v equals to v pi? Does v equal v pi? Okay. So maybe you can pause the video for a couple of minutes and just think about it, and then let's discuss the solution. So the claim is that, yeah, this pen is giving some issue today for some reason. Okay, but the claim is that v equals v pi if and only if v is an optimal value. So let's try to prove this. So suppose v is an optimal value function. Okay. So if it is an optimal value function, it will satisfy the Bellman's equations corresponding to the optimal value function, which is that VSS RS plus gamma times max over A sum over S prime. Okay. V of S prime given as A, V of S prime. So it's going to satisfy this, right? And now how do we compute pi s? Well, we compute pi s as R max over A sum over S prime V of S prime given as A, V of S prime. Right. So the action which maximizes this quantity, that is chosen to be pi s. So this is the action which maximizes this. So since pi(s) is the action which maximizes this quantity, so what I can do is that instead of max of A and then picking that action, I can just substitute this as pi of s, right? So therefore, I can rewrite this equation as V of s is Rs plus gamma times sum over s prime, P of s prime given s and pi s, P of s prime. Right? Because pi s is the one which is maximizing this, and I wanted to pick the action which maximizes it. So I can just pick pi s, right? Because that's the definition of bias itself. And now what do you see, right? So this is the Bellman equations according to which follows the policy pi, right? So the solution to this is V pi, and we see that V is also a solution to this. Therefore, by uniqueness of solutions to Bellman's equation, we must have V equals. So if V is an optimal value function, then essentially from V, if you compute pi, and then from pi, if you compute V pi, then V and V pi are going to be the same. Okay. Now let's look at the converse part. So suppose V equals V pi. Okay. Then what's going to happen? Okay. So now V pi must satisfy the condition that V pi of S is Rs plus gamma times sum over S prime P of S prime given S and pi S V pi of S prime. Right. But now since V is V pi, okay, so if instead of V pi, I can just rewrite it as V. Right, because V is V pi, so I can just write it as V. And now pi s by definition is argmax over A sum over S prime P of S prime given S A V of S prime. So pi s is the one which maximizes this quantity. So what we can do is just instead of pi s, we can write a max over A, right? Because pi s is the one which is maximizing this expression. So what we can rewrite it as V of S is R of S plus gamma times max over A sum over S prime P of S prime given S A P of S prime. Okay. So what we get is that V is the, and this is now the Bellman's equation corresponding to optimal value function. So therefore, what we get is that V must equals V star or the optimal value. So therefore, if you follow the steps that from V, if you compute pi and from pi, you compute V pi. So if V and V pi are exactly the same, then essentially that means that you have an optimal value function. And that is exactly the idea behind our algorithm, which we are now going to rewrite, right? So now you would have like sort of gotten some intuition about the algorithm, right? Even before we have given the algorithm. So basically, this is a policy iteration algorithm, which I'm going to discuss now. So the way it works is as follows. So firstly, we initialize a policy pi randomly. Next, we repeat the following steps until convergence. What are these steps? So firstly, you evaluate v pi. Okay, next you update pi as to be argmax over a sum over s prime p of s prime given as a b pi of s prime. Okay. So from the policy you compute p pi, from the v pi you recompute the policy, right? And you keep on repeating these steps until convergence, right? And essentially this is our entire algorithm. Now the claim is that if the above algorithm converges, then V pi is the optimal value function, right? With pi as the optimal policy. And the proof is something we have already seen, right? Because the two steps which we are performing are same as the one we discussed for V being equal to V pi just in the last 2 3 slides. Right? So if the above converges, okay, then V pi is the optimal value function, okay, with pi as optimal policy. So this is essentially our policy iteration algorithm. And we have seen that if it converges, then essentially we'll get an optimal policy as well. Now the question is that, does it converge? How many iterations will it take to converge? So we'll discuss that now. So the first claim is that the number of policies is finite. Right. So assuming, of course, finite state space and finite action space. Right. So if the number of states is mod S, the number of actions is mod A, then essentially this is upper bounded combinatorially by mod A to the power. Because for every state you can choose mod A such actions, there are mod S such states. So you have mod A to the power mod S combinatorial possibilities. The next claim is that you cannot cycle when you are performing this algorithm, right? So if either you converge or you get a new policy. So how do we show that? So the next claim what we are going to say is that so each step there's some issue with pencil today, but so each step improves over V pi. Okay, so that is V pi t plus 1 s is greater than equal to V pi t s for all. So how do we show this? So suppose pi is the policy being followed at step t with the value function v pi. Okay. And let pi hat be the policy followed at time step t plus 1. Therefore, pi hat of S is now R max over A sum over S prime P of S prime given SA V pi of S prime. And now we consider a hybrid policy pi hat 1. Okay. So now our goal is to show that V pi hat is greater than equal to V pi. So that's our main goal. Show that V pi hat is greater than equal to V pi. So how do we do that? So what we are going to do is that we are going to consider some intermediate steps. So we'll define in general, we'll define a family of policies, a family of hybrid policies. This which we are going to denote by pi hat n, wherein pi hat or pi t plus 1 is followed for first n steps, after which the policy pi is followed. Okay, so for first n steps, you follow pi hat and then you follow pi. And now we are going to show that each of them they form an increasing sequence. So let's try to prove that. So what we'll try to now do is that we'll inductively try to show that V pi hat n is always greater than equal to V pi hat n minus 1. So here essentially pi hat 0 is essentially nothing but pi, right? Because if you follow pi hat for 0 steps and then follow pi, so essentially your policy itself is pi. So let's try to inductively show. We'll show inductively that every step of this pi hat actually improves our value. Essentially, V pi hat of n is greater than equal to V pi hat of n minus. So let's try to show the base case first. So basically that V pi hat 1 of S is greater than equal to V pi of S for all S. So how do we show this now? The base case. See what is V pi hat 1 of S. So V pi hat 1 of S, the value function, if you follow pi hat for the first step and then follow pi from then onward. So firstly, you just get reward as it is, R of S. And then you have gamma times sum over S prime. So since in the first step, we are going to follow pi hat. So the next state which we'll be moving to will have distribution given by P of S prime given S and pi hat of S. And after that, the value function which we are going to use is nothing but V pi of S prime. Right? So this is what we have. And now we know that this is going to be greater than, right? So basically, what is pi hat S? How is it chosen? So pi hat of S is chosen to be max over A of this quantity. So pi hat of S is nothing but max of this quantity, R max of this quantity. So pi hat S is the action which maximizes this quantity, right? That's the definition of pi hat S. Right? Because at every step, we compute pi hat as this quantity. So this is nothing but R of S plus gamma times max over A sum over S prime, P of S prime given SA and V pi of S prime. Now this is the action which maximizes it. So therefore, if I choose any other action, let's say I choose this action according to the policy pi, my original one, right? So then this will be greater than equal to p of s prime given s pi s v pi of s. Why? Because essentially here this is the action which maximizes this quantity, and pi is any arbitrary action like any other action. Right? So this is greater than equal to the value if I substitute a to be pi of s. And now by Bellman's equation, since V pi s satisfies the Bellman's equation, this must be equal to, okay, this is V pi s prime, but this equation must equals V pi s by Bellman's equation. So from here, what we get is that V pi hat 1 of s is greater than equal to V pi s for all s. So this essentially proves the base case of our induction, wherein we want to show that V pi hat n is greater than equal to V pi hat of n minus. Now let's make the inductive hypothesis that let this particular equation be true until some n. Okay, now we'll want to show it for the next n. Okay, essentially let's say this is true for n minus 1. Now we are going to show it for. So let pi hat n. Okay, so now we want to show that assuming it is for true for n minus 1. Now we want to show that v pi hat n is greater than equal to v pi hat n. So let pi hat n be the policy which follows pi hat for n steps and then follows pi. Okay, so this satisfies the equation that v pi hat n of s is nothing but r of s plus gamma times sum over s prime p of s prime given s comma pi hat s. So firstly, we are going to pick pi hat s. And now we have the value function where pi hat is followed for the first n minus 1 steps and later pi is followed. And that is v pi hat n minus 1 of s prime. Right? So now this is now by induction hypothesis, v pi hat n minus 1 of s prime is greater than equal to v pi hat n minus 2 of s prime. Right? So therefore, this is greater than equal to rs plus gamma times sum over s prime p of s prime given s and pi hat of s, right? B pi hat n minus 2 of s prime. Right? And now once we substitute n minus 2, what we get overall is this is the equation which was satisfied by v pi hat n minus 1 of s. So essentially v pi hat n of s is always greater than equal to v pi hat n minus 1 of s. So this gives us a chain of inequalities, which is that v pi hat n is greater than equal to v pi hat n minus 1 and so on until v pi hat 1, which is greater than equal to v pi. So v pi hat n is always greater than equal to v pi. And if I take limit of n approaching infinity, v pi hat of n s, that is also going to be greater than equal to v pi of s. Right? So it's going to be greater than equal to each of these v pi hat n as well, and it will be greater than equal to v pi of s. But if I take this limit, what do I have, right? So if I follow it for infinite number of steps, then it means that I'm following pi hat always. So therefore, v pi hat s is greater than equal to v pi s. So basically, pi was the policy at time step t, and pi hat is the policy at time step t plus 1. So essentially, if you go from step t to t plus 1, you will always improve the value function. And hence, we can see that every step is going to improve our policy. Basically, it's going to either remain the same or improve. We cannot decrease. So essentially, if you go from pi t to pi t plus 1, then essentially v pi t plus 1 is always greater than equal to v pi t. But what we can ensure is that there are no cycles, right? So it can't be that you change from one policy to the next and then the next and next and then you come back. So there cannot be any cycles. You can only improve, right? But we have also shown that number of policies is finite. Assuming finite state space and action space. Therefore, we must converge. So now we have seen two algorithms. One is policy iterations, wherein the number of steps to converge is exponential, but we are guaranteed that we'll get an exact solution. However, the only issue is that the number of steps could be much larger. It could be exponentially large. And then we have the other way of value iterations where the solution is approximate. So which one of these is better? Well, the idea is that for smaller state space, you can do policy iterations. For larger ones, you will have to do value iterations. Because firstly, every step involves computing vpi, and we know that computing vpi will take order n cube time, and it's the number of states, and also it's the number of steps in general could be in worst case exponential, but that's only the worst case, right? For typical cases, you won't go in exponential. But again, still that n cube time will be there, and it might give you a hindrance for larger state spaces. In practice, what you may want to do always, what you may want to do is the hybrid approach. So hybrid approach involves, doing policy iterations, but rather than computing vpi exactly, so you can run few steps of Bellman's equations, okay, for policy pi. And if you only update the policy for a few states only, then essentially you may not need to do those iterations, those iterations for computing vpi for all the states, right? You can only look at some of the states. So there are some of these hybrid approaches as well. I'm not going to go into too much of detail, but I just wanted to give you a hint at that. Okay. Now that completes, the basics of this Markov decision processes. Now we are ready to go into the real world of reinforcement learning, wherein the environment is not known to us. Before that, we may want to look at some of the bandit algorithms, okay, wherein to see how that uncertainty, how that comes up when if you do not know the environment fully. So that will be the plan for the next few lectures. Hope you liked today's lecture, and thanks a lot, and goodbye.